So, my project was a fuel loading analysis of the Steffen Center Forest, which is a small stand on the WSU campus. So, the stand is mostly used for research and field training by the students for educational purposes. It sits at the east end of Pullman and has a north aspect. It's a little under 6 acres. The site sits within the wildland urban interface, so it's adjacent to university buildings and roads and a grassland. The site has high use by humans and wildlife, and because of this and its position in the landscape, it calls for effective fuel management to mitigate for fire and other disturbances. It's in the Palouse Hills mesoclimate, and it's a ponderosa pine Idaho fescue association, and there is a lodgepole component as well as a sparse grass layer with another small blue bunch wheatgrass component. There are passerine songbirds, woodpeckers, owls, deer, and rodents. And this is a planted stand that's fairly uniform at about 45 years of age. Here's some images from when I was doing my field work. So, the purpose for analysis was to really get a hint at how to manage to mitigate fire in a sensitive area with high use by humans and animals in the wildland urban interface. So the analysis should describe the fuel loading and hint at management techniques. So because this is a small, planted and fairly uniform plot, I thought a systematic grid sampling method would capture the variability on the site. So transects were spaced at 2 chains, and plots were spaced at 2 chains along the transect, making a 2 chain by 2 chain grid. The sampling plane lengths were 60 feet, and I used 1/100th acre plots for canopy sampling. And in the image here, the pins represent plot centers, and the lines represent the brown sampling planes, 2 per site in randomly oriented. My materials were pretty basic for this analysis. I used a tape measure for size classes and dBH, and a string to measure stem circumference for dBH. My cell phone tracked movement and recorded data through Avenza Maps and Excel. And then I used a compass with an angle measurement for navigation, slope, and tree height calculations. For find dead fuel moisture, I use the lookup tables in the NWCG handbook in Appendix B. For the 1 hour time lag, I use the adjustment factors from the same handbook based on the state of weather code. And for a 10-hour time lag, I use the Symerd equations, 1968, excluding the fuel moisture sticks. For surface loading, I use the Brown 74 planar transect method. Slope, intersecting fuels, 1,000-hour diameters, sampling plane lengths were all recorded in the Brown's fuel loading calculator. 2 random direction sampling planes were walked per plot, and the sampling plane lengths were 1 and 10-hour fuels were 6 feet, 100-hour fuels were 10 feet, 1,000-hour fuels were 60 feet. For canopy loading, as I mentioned before, the plots were spaced in a 2 by 2 chain grid with 1/100th acre plot sizes. I used the Brown 1977 allometric equations and lookup tables with adjustment factors from Reinhardt 2006 to calculate tree loading, single tree loading, and then extrapolated that data by a factor of 100 to find the loading per acre. For modeling, I used Behave Plus, and I used Fuel Model 9 as the input, which was longleaf pine or hardwood litter, which I felt closely matched my site. The fuel moisture data was entered, and a 4 mile per hour mid flame wind speed was used, which was the wind speed the day I was in the field, and then an average slope of 30% was used. So, because the stand was small and has a single aspect, it's fairly uniform coverage, and there's very little elevation change. I thought it was safe to assume that there's insignificant variance in moisture content across the plots. So here was the fuel moisture for the site. For surface loading, one interesting result that I got was high variance for the 1,000-hour sound fuels. And I believe that this was the case because of how the logs were grouped into burn piles throughout the stand. So there were large stretches with no logs and then some with piles of logs. The results for canopy fuel loading showed the majority of loading in the 10-hour fuel class, which I believe is due to the size of the limbwood of the ponderosa pine, which was dominant in this stand. The modeling results showed a fairly fast rate of spread for surface fire, but a moderate flame length. And with a fairly high CBH across the stand and a 4 foot flame length, the stand seems to be fairly resilient to a canopy fire. Although if a burn pile were to catch, a tree may torch after that. But all in all, a fast, flashy surface fire is what is expected in this stand. There was some variability in the fuel loading that was not captured by this study. I never actually counted or sampled a fallen tree, even though there were a few of them across the stand. So that was one issue with the study. Um, in terms of fuel moisture, the stand was well shaded, and at this time of the year, moisture is retained fairly well. The surface fuel analysis generally found more loading in the larger time lag classes. Surface fuels were mostly comprised of litter and logs or fallen trees. The canopy fuel analysis showed a vast majority of loading in the 10-hour time lag classes, most likely due to the dominant ponderosa pine. The modeling through Behave Plus showed moderate fire behavior and fairly low chance for high intensity fire behavior, which was to be expected. Um, the stand is even aged with a high CBH, low surface loading, and all these things tend to lead to a fire resistant stand in the wildland urban interface. And these are my references. Thank you.